Hey everyone, welcome to my channel. In this video, let's solve another interesting problem, top k frequent elements. So first we'll understand the problem statement, then we'll look at a couple of different ways to solve the problem, then we'll look at the runtime complexities for each of the solution, and finally we'll look at the code implementation. So let's dive into the problem now. Okay, so here we are given a list of integers and a positive integer k. So from this list, we have to find the top k set of numbers. So what do I mean by that? So from this list here, I have marked each number and its frequency. So since k is equal to 2, we have to find the top two numbers. So the top two numbers from this list are 10 with a frequency of 4 and 70 with a frequency of 3. So this is the expected output. So how do we solve this problem? Okay, so one of the ways to solve this problem is to iterate through these n elements and create a hash map of each unique number and its frequency. And from this hash map, sort these unique numbers based on the frequency, create an output list, and from that output list, pick the top k elements. Now this is a good solution. But what is the time complexity of this solution? To iterate through these n elements, the time complexity is big of n. And to sort these m unique numbers, the time complexity is big of m log m, where m is less than or equal to n. M is the number of unique elements in the given list, and m is greater than or equal to k. Now in the worst case, m is equal to n. In that case, the time complexity is big of n log n, big of n plus n log n, and for large values of n, this will subside big of n. So the overall time complexity is big of n log n. Now this is a good solution, but can we do better than this? Can we solve the problem in big of n log k time? So yes, we can. We can solve this in n log k time using a data structure called priority queue. So let's see how we can do that. Okay, the idea here is pretty simple. We iterate through the keys of the hash map and add them to a priority queue or a min heap based on the frequency. Now whenever the size of the priority queue reaches k, we start removing the minimum element from the priority queue, that is the element with the least frequency from the priority queue, and add the remaining keys from the hash map. Now at the end of iterating through the complete keys of the hash map, we will have the top k frequent elements in the priority queue. So let's see how this works now. Let's add the first key, which is 10, with a frequency of 4 to the priority queue. So I'll mark the frequency also for our understanding. Okay, now the next element is 20 with a frequency of 1, so we'll add it to the priority queue. Now this frequency is less than 1 is less than 4, so the priority queue will rebalance, that is we'll call the heapify function, and this will move to the top. So this is 20, 1 and 10, 4. Okay, now let's move to the next element in the priority queue, in the hash map. So this is 40, 2. So we'll add 40, 2 to the priority queue. Now this frequency is greater than 1, so the priority queue is balanced. But the size of the priority queue is 3 and this is greater than 2. So we have to remove the least frequent element from the priority queue. So that is the top of the priority queue. This is 20, 1. So let's remove this, and the priority queue is rebalanced and this will move to the top. So this will be 40, 2 here. Okay, now let's move to the next key in the hash map. So this is 50 with a frequency of 1. So this frequency is less than whatever we have at the top of the priority queue. So we don't need to add this to the priority queue. Okay, let's skip this element and move to the next one. So this is 70, 3. So we can add this to the priority queue. Now the frequency 3 is greater than 2, whatever we have at the top. So the priority queue is balanced. Now the size of this priority queue is 3 and k is equal to 2. So again we will remove the top element of the priority queue and move this to the top. So this will be okay. Now we have iterated through all the keys of the hash map and we have a priority queue with the top k frequent elements. So that is 70 with a frequency of 3 and 10 with a frequency of 4. So this is the expected output. Now, what is the time complexity of the priority queue solution? So here at any given point of time, we see that the priority queue contains at most k elements. So insertion or deletion to the priority queue takes log k time per insertion or per deletion. Now there are m unique elements in the hash map. So it takes m log k time to iterate through the hash map and add all of the keys of the hash map to the priority queue. So this is big of m log k. Now in the worst case, m is equal to the size of the input set, which is n. So this is n log k. So this is the time complexity, and this is better than the sorting solution, which is n log n. Now what is the space complexity of this solution? So in the worst case, we add all these n elements to the hash map. So we need to store n elements to the hash map, so that's big of n. And at the same time, we'll have k elements in the priority queue, so that is big of n plus k. So this is the space complexity. Okay, now this is all theory. So let's take a large input set and compare the running times of the priority queue solution with the sorting solution and see which one is better. So let's dive into the code section now.
Okay, so the code section this time around is really interesting because we shall find the top k numbers using two different methods, the sorting method and the priority queue method. And the input size here is really large. That is, it's 10 million random numbers. So let's check the performance of both the methods. And there are a couple of different input files. The first file will contain 400,000 unique keys, that is unique numbers, and they repeat. The second file will contain 10 million random numbers, and each of occurs only once. Okay, now let's look at each of these functions. So the first function is read from file. So this is pretty simple. We are reading these random numbers from these files and adding it to this nums array. Pretty simple and straightforward. Okay, and here we have a function called create hash map. So this is where we are creating a hash map of each number. So we are creating through this nums array. So we are creating a hash map of number and its frequency. So how many times it occurs. And this hash map here is a static map, and we shall use this hash map for the comparators, the priority queue and the sorting comparator. Okay, so here this part is where we'll find the top k elements using the sorting method, and this part here we'll find the top k elements using the priority queue. Okay, so first look at this method here, find top k by sorting. This is pretty simple. I'm using a collections.sort method, and I'm passing in the sorting comparator. So here I'm sorting the numbers based on the frequency, and what I'm doing here is the numbers are sorted in the descending order based on the frequency. So this is pretty simple. So here, once we have the numbers sorted based on the frequency in the descending order, then we'll pick the top k elements from that list. So we'll add it to the output array. This is pretty simple. Okay, now let's look at this find top k by priority queue. So this is the main algorithm that we saw in the whiteboarding. So here I'm creating a priority queue, and the comparator passed to this is the priority queue comparator. So here also we are using the map for the comparison. So we are adding the elements to the priority queue, the numbers to the priority queue based on the frequency. Least frequent number will be appearing at the top of the priority queue. That's what we are doing here. Okay. So like I explained in the whiteboard, basically. So here we are iterating through each of the number in the hash map. Now, first thing what we do is we'll check if the queue size is equal to k, and if the number in the hash map, if it is less than the top element of the priority queue, then we don't need to add that number because we know that it is lower than the element at the top of the priority queue. So we'll skip that number. Else we'll add it to the priority queue. Now if the size of the priority queue at any point is greater than k, then we just remove the top of the priority queue, that is the number with the least frequency. Okay, at the end of iterating through the hash map, we will have the top k elements in the priority queue. Okay, and then we will poll those elements from the priority queue and then add it to the output array. So this is pretty simple. Okay, now let's run them. Run the first file, that is input1.txt, and see which one performs better. From the theory, we know that the priority queue method should be faster, but let's see what happens. So I'll run this. So here, like I said, there are 400,000 keys, and the sorting method took 95 milliseconds, and the priority queue method took 126 milliseconds. So what we see is this is different from theory, right? Okay. The reason is if the keys are smaller, then the sorting method is faster compared to the priority queue method. Now let's look at the other input file. So this input2.txt will contain 10 million random numbers, and each number is unique. So there is no repetition. So what the output here is the number and its frequency. So yeah. So let's look at the next input here, and then we'll run for input2.txt. We'll run and see what happens. Okay. So here you can see that the number of keys here are 10 million. That is, each number is occurring only once. The sorting method took 1281 milliseconds to finish, whereas the priority queue method took 867 milliseconds. So as the number of keys increase, the sorting method fails, or the sorting method is slower. So priority queue method is faster, like we saw in theory. So this is n log k, and this is n log n, basically. Okay. Um, So thank you so much for watching this video. If you learned something new, please to hit the like button and subscribe for more videos. Thank you. Bye.